Okay, welcome. It's Professor Elliott. In this video, we will be solving the common emitter AC amplifier. So there's your circuit. Please take the time to make a copy of this. You will need it. The only thing I need to add here of course, that's where the output voltage is coming from, and R3, if you prefer, is RL. So you can make a copy of that, and then we'll continue on. Okay, welcome back. Let's continue on. So this is the steps to solve for RTH and VTH, the Thevenin resistance and Thevenin voltage respectively. And we've done this before, so this should be just review. Okay, so you can take a copy of that if you want. Okay, so RTH is simply going to be R1 compare with R2. Okay, make sure you're looking at the schematic. So that's going to be 15K in parallel with 3.3K. And that gives us 2.7 kilo ohms. VTH R2 over R1 plus R2 times VCC, 2.7 volts. Okay, so those are the two values. Substitute in there. Okay, R in base is the resistance looking into the base of the transistor. So that's going to be beta AC times RE, beta DC. So that's going to be, let's let beta equal 100. Yeah, so let's go 100 times 560 ohms gives this current base 56 k ohms. R in is looking into the voltage divider, sort of from left to right. So that's going to be RTH plus RN base equals 2.7 plus 56 equals 58.7 k ohms. Okay, IB is VTH minus VBE divided by RN. So that's going to be 2.7 volts minus 0.7 divided by 58.7 k ohms. And that equals 34.07 microamps. Okay. Okay, so there's the model. That's where the formula came from. Of course, then IC, which is virtually equal to IE, equals IB times DC beta. So that equals 34.07 times 100 equals approximately 3.41 milliamps for the collector. Okay, the AC model. Okay, so we replace each capacitor with a short circuit because the capacitor reactance, the capacitor value is selected such that over its reactance over the frequency range of the amplifier is approximately 0. Short VCC to ground, and just redraw what you see. Okay, take a picture of this because we're going to be needing it for the remainder of the presentation. Okay, here we go. Z in base. Okay, so Z in base is going to be the impedance looking into the base of the transistor. So that's going to be beta AC times R prime E. Okay, so we're going to let the beta AC, just picking numbers here, 130. R prime E is the standard formula, 25 millivolts divided by IE, and that gives us 0.025 divided by 3.41 equals 7.33 ohms. So 7.33 ohms times 130. So 7.33 times 130 gives us 952.90 ohms. Okay, and again, make sure you're looking at the original schematic and or the AC model, because otherwise that doesn't make any sense. And so that's what that value is. Okay. Zn is equal to RTH in parallel with Z in base, and that was 2.7 in parallel with the 952.9 ohms is 704.43, I believe. Let me just quickly check. That's all right. So 704.43. Okay. So that's going to be that. Okay. All right. So in order to calculate the voltage gain, we need to calculate the output impedance. So that's looking back into the collector like that. So obviously Z out is simply RC in parallel with RL, which in this case is R3. Okay, so we have 1.2K divided in parallel with 4.7K. So that gives us 955.93 ohms. All right, voltage gain. Okay, so this is the amplifier, this constant current model. That's the symbol for a constant current source, which is essentially what the BJT is. Okay, so this would be ZO, VO, collector lead, prime E, emitters at AC ground. Okay, this is the base lead. Okay, so therefore we can say then that AV equals minus ZO divided by R prime E. This simply means the output's 180 degrees out of phase with the input. So the output impedance again was 955.93 divided by R prime E, 7.33. Okay, so that equals minus 130.41. Which means 180 degrees of phase with the input. Okay, all right, so we can convert that to a dB. So that equals 20 log AV. So 20 log of the 130.41 number. Drop the negative, please. I'll put a negative here. 42.31 dBs. So gain is expressed either in decibels or a ratio. And AV is simply equal to VN sorry. There we go. VO is equal to the voltage gain times VN. So that's use the ratio, not the dB. 130.41 times 20 millivolts. And it didn't say anything else, so the 20 millivolts is an RMS. And you can convert it to peak or peak, whatever, if you need to. So 20 times 130.41 equals 2.61 volts. Okay, so that would be the output. Wrong way, sorry. All the way back. See here, I've included the source resistance. So that means then which is right there. So we need to calculate what is the AC voltage at the base. So we know Zn, we know Rs and Vn. Rs is the source output impedance at 120. Okay, so let's go continue on with that. Okay, so we can say that including Rs, the AC voltage at the base of the transistor is simply going to be Zn divided by Zn plus Rs times Vn. Okay, so Zn was the 704.43 divided by 704.43 plus 7.33 equals times 20 equals. So because of it's a practical source, so we're considering its output impedance. Okay, small voltage loss. So actually in the base we're getting 19.79 millivolts. And it's not a big difference versus the 20 millivolts here. Okay, so the circuit as presented, the actual voltage, and then multiply that by the gain, would be 2.58 volts at the output, 2.61. And the difference is the small voltage loss across RS. Okay, so finally, this is not to scale by any stretch of the imagination. Okay, so this would be Vn, like that, and this would be VO, and let's go for this color here. Okay. I don't know. We want to use let's use black. Okay, so this would be VO, and it's 180 out of phase. Okay, so that's what that means. Okay, and then you could convert this to the peak voltage, and you can convert this to the peak voltage from the RMS. Okay, but you can see the input and output are out of phase, and the output is 130 times larger than the input. Okay, so I think that's the end, and thanks for watching this video, and I hope it helps you out. Okay, bye, cheers, see you later.